Okay, so here we are for the final unit of AP Physics 1. This is Unit 7, where we're going to look at rotation. As you can see, we may deal with the rotating Earth. You'll see there's a lot of overlap between kinematics, as well as we'll do some angular momentum. We'll explain why figure skaters spin faster when they're tighter and or slower when they're larger. Okay, in this video, we're going to look at the first kind of section in this unit, which is going to focus on rotational kinematics. So we're going to lay out a lot of the basic terms for this unit here. Um, and we're going to relate it back to our linear kinematics. All right. So the first thing is, up until this point in AP Physics 1, everything we've been doing has been traveling in a straight line. Now, that straight line could be something that looks like this. It could look like this. Even though this looks more like a circle or a semicircle, this is a straight line, right? You can do uh, something crazy like this. But again, we're not rotating the object, right? Or you can take, just a simple path, go up in an angle, back down in an angle. Okay. But what we're going to do now is we're going to fix the axis of rotation. Okay. We're going to move things around a set point that we call the axis of rotation. Right? And so therefore, instead of objects traveling in a straight line, they will now rotate. Right? Instead of doing this, they're going to spin. Okay, it could be Earth, it could be a merry-go-round, it could be any kind of amusement park ride. Okay, the first step in describing motion, right, just like we did with Unit 1, the linear motion, we described it, right? So the first thing we're describing is that we're going to define what is known as angular position. Angular position is given as theta. Okay, again, you see this word angular. If you remember anything from math, it pretty much goes back to theta. Now, one thing to note is that the signs of angular position or angular anything, okay, counterclockwise is our positive direction, clockwise is our negative direction. So what they basically say is that um, clocks are backwards, right? In physics. So and the reason why is because if you think about the unit circle, yes, we have to go all the way to math. Note that the angles are positive in the counterclockwise direction. Okay, so that's why the positive direction is counterclockwise. Now, the SI unit for angular position is radians, or we abbreviate that rads. Now, you don't have to put your calculator in radians here, okay? Because we're going to use this, we're going to treat this like meters, okay? Um, and so a radian is the angle for which the length of a circular arc is equal to the radius of the circle, right? So if you remember, it's going to be 2 pi radians equals 1 revolution, rotation, okay, or anything like that. All right. Uh, and so I should have, that's later, okay. But what happens is multiplying the angle in radians by the radius gives us what we call the arc length. And so if you, these are just some terms that you may have remembered from, basic geometry courses. So arc length is S, right? But we'll actually call this X. Mathematically, it's going to be X equals R theta, right? Math would have been S equals R theta. But again, we're going to relate this back to linear, okay? Now, in 1 revolution, which is a complete trip around, an object will rotate 1 complete circle and travels the circumference of that circle. Circumference, right? And the conversion factor is 2 pi rads equals 1 revolution. We talked about that. And wanted to note is when you do conversions in math, they do pi radians, right? So they only focus on half the circle, where here in physics, we're going to focus on the full rotation. Now that we've defined angular position, we can now start focusing on what happens when we change that angular position. Okay, so the change in angular position is known as angular displacement. Right? And all we really do is displacement becomes delta, right? Delta theta. So mathematically, it's theta, delta theta equals theta minus theta initial, right? So initial angular position minus final angular position. Sorry, backwards. Final angular position minus initial angular position. Now, if this occurs over time, the object is now rotating with an angular velocity or an angular speed. All right, and we give it the symbol omega, right? So this is the Greek letter omega. It's the lowercase omega. Keep right on the right an end. Now the capital omega is that cool horseshoe-looking one. Okay, mathematically, omega is defined as change in angular velocity over change in time. And the SI unit for angular velocity is simply radians per second, or rads per s. Now you do have to understand, um, you may see RPM, which is revolutions per minute, okay, which means you would have to convert between them. Now, again, the direction is going to follow as before. Positive is counterclockwise, negative is clockwise. And so here's just a simple a simple example. So we got an antique long playing phonograph record, right, rotating at 33 and a third revolutions per minute. What is the angular velocity in radians per second? So this is just really a conversion. So we're going to do 33.3333, right? And that's going to be radians per minute. And so these are the big records, right? Because the little ones are 45, so they rotate at 45 revolutions per minute. So we're going to say 1 revolution is 2 pi radians, and 1 minute is 60 seconds, right? So if I go through, do a little bit of that dimensional analysis stuff that you guys will cringe about from chemistry. So the only thing left will be radians and seconds. And so do my math, and we end up that this is going to be 3.49 radians per second. Okay. Again, this is really looking for the, if you want to say angular velocity, we'll just call this positive, right? We'll just say that it rotated counterclockwise. Now, note that any instant that you're moving rotationally, you are traveling in a direction that is tangential to the circular path. All right. To find your tangential speed, divide the distance corresponding to the circumference of the circle by the path time required to complete one circuit. So the tangential speed is going to be the circumference of the circle divided by the period. And so, in fact, the quantity 2 pi over t is another way to write the angular velocity. Therefore, you can determine the tangential velocity by simply using v equals r omega. So you kind of see, if you go back to the um, s equals r theta, right? It's got kind of that same factor of the radius. And so now let's look at an example. So you got a CD, basically a CD is going to tell us that it's moving at 1.25 meters per second. And as the CD is played, the laser beam scans the disc. And what angular speed must the CD have when the laser beam is shining on the disc at 2.5 centimeters and 6 centimeters? So basically, we're going to use this V equals R omega. We're going to solve this for omega. So it's going to be V over R. Again, this V is going to be our linear speed. And so basically what's happening is, right, this is spinning. We'll just call it that way. And we're looking at how fast is it moving here. And let's say all the way out, right? Because or 6 centimeters and 2.50 centimeters, right? So they're gonna, even though they're spinning rotationally, or even though technically they should be spinning at the same rate, you're gonna see that it's gonna be based on their position, okay? And so if I convert this to meters, 0.0250, it's gonna tell me that it's spinning at 50 radians per second at 2.5 centimeters. Now we do the same thing for V over R. Um, for at 6 centimeters, so we're going to do 1.25 meters per second divided by 0.06 meters. and you're going to see this gives us a linear speed of 20.8 radians per second. So you can kind of see that the further you are away, the slower you're going to the slower you're going to be in terms of your rotational um, velocity. All right, so here are your relationships. V is directly proportional to R. It's also directly proportional to omega, but R is inversely proportional to omega. Gotta choose my pen, not my eraser. All right, and so if I'm closer to it, if I'm closer to the if I'm closer to the center, I'm going to go faster. If I'm further away from the center, I'm going to go slower. All right. Now, and so this last little thing, we're going to talk about angular acceleration. So a rotating object accelerates, right, if its rate of spinning changes, right, and this is known as the angular acceleration, which is given the symbol alpha. So if you look at kind of like how do we relate these, you can see that we're just given uh, the linear quantity a Greek symbol, right? So we're going to distance is theta, velocity is omega, and now you can see acceleration is alpha, right? So they all correspond. So more specifically, the angular acceleration is the rate at which angular velocity changes with respect to time. So mathematically, it's going to be change in omega over the change in t, just like we've done before, right? This is really a definition equation, and the unit is going to be radians per second squared. And so just like what we did linear, so you see there's a lot of go between, or a lot of similarities between linear and rotation. So if omega and alpha, this is an alpha, not an A, are in the same direction, the speed of rotation is positive. Okay. In fact, it is increasing, is what we should say. And if they're in the opposite direction, okay, the speed. In fact, let's get rid of positive, and we'll get rid of these parentheses. So that means that the speed will decrease. So just like when linear, if they work with each other, the speed is going to increase. If they work against each other, they're going to decrease. So here's just an example problem. So the wheels of a car speed up from 5.2 radians per second to 7.9 radians per second in 1.3 seconds. What is the angular acceleration of the wheels? So again, this is just a definitional problem. So we're going to do change in omega over change in t. So it's going to be 7.9 minus 5.2 over 1.3. And we're going to find that it's going to be a positive 2.1 radians per second squared. And that looks like a V. So let me rewrite that. Now, just like we did before, we related the linear to the rotation. So there's a relationship between what we call the tangential acceleration and the angular acceleration. And it's just going to be A acceleration equals R alpha. And sometimes you will see like a little subscript T there just to talk about tangential. So in the next video, we're going to talk about, and we're going to relate the rotational kinematics equations to the linear kinematics equations.